The Terrestrial Brachistochrone by Matt Vancouvering and advised by Dr. Amy Colin. Scientists have theorized many ways of transportation that have yet to be realized. One of these theories is that of the gravity train, a system in which an object, such as a train, can travel between 2 points on Earth's surface with very little external energy input. The system works by using the force of gravity and the law of conservation of energy. In this presentation, I will first look at a linear path through Earth. I will show that by taking this path, the travel time is a constant 42 minutes, or thereabouts, no matter where you're traveling to and from. I will then derive the equations for the Brachistochrone, the path of least time, and compare these results to the equations of a hypocycloid, thereby showing that the path of least time through Earth is the path of a hypocycloid. Finally, I'll compare the results of a linear path to the results of the hypocycloid path. In this diagram, which is an oversimplification of Earth, we can see the linear path through Earth from A to B, where the train is the red dot. The train's position x is the distance it is away from the start position A. Note that initially theta is at a minimum, and as it increases, the distance between the train and the center of Earth decreases, where we reach a minimum distance, r0, at the midpoint of A and B. At a certain distance r from the center of Earth, there is an external shell and an internal sphere. We use Newton's shell theorem, which states that if a body is a spherically symmetric shell, which we assume it is, no net gravitational force is exerted on an object inside the shell. Therefore, the force of gravity on the train is only due to the internal sphere. Assuming uniform density, we're able to compute the mass of the internal sphere as such. Using Newton's law of gravity, we can find the equation for the force of gravity on the train at any distance r from the center of Earth. Note that the force of gravity grows linearly with r. Looking more closely at the geometry, we are able to derive the equation for the component of the force of gravity along the path. By using Newton's second law, F equals ma, we arrive at a second-order differential equation, which is easily solved by separation of variables and integrating. Assuming the velocity of the train at the surface of the Earth is 0, we get the following first-order differential equation. This again is solved by using separation of variables. Since the path is symmetric about its midpoint, we define the limits of the integrals as such. We then find that the total time it takes the train to get from A to B is approximately 42.2 minutes, which is independent of start and end points. We'll now watch a short VPython simulation of the train moving along the linear path. Now that we have covered a linear path through Earth, let's find the path of least time. Recalling our force of gravity equation, we are able to derive an equation for the potential energy of the train at any distance r from the center of Earth. Using the law of conservation of energy, and firstly assuming that the velocity of the train at the surface of Earth is 0, and secondly that no energy is lost to friction, we are able to solve for the velocity of the train as a function of r. Using our equation for velocity and the above equation for ds, we are able to define the integrand of the time equation as such. Recall that we want to minimize the time it takes to get between 2 points, and so, by noting that the integrand doesn't explicitly contain theta, we are able to use an alternate form of the Euler-Lagrange equation to get the following equation. We can solve for the constant c by noting that when r equals r0, dr d theta equals 0. Thus, we get the following expression for c. Equating these two equations, we get an equation for dr d theta. We are able to solve this differential equation with separation of variables and integrating. Note that the theta angle has been redefined for simplicity. This doesn't change any of the previous results. Making a clever u substitution, we can simplify this result and integrate, resulting in an equation for theta in terms of r. For further simplicity, we introduce a new variable phi. Directly from this definition of phi, we are able to get an equation for r with respect to phi, and by plugging in our substitution into the above theta equation, we get the corresponding theta equation in terms of phi. We now want to show that these equations of motion for the path of least time are that of a hypocycloid. A hypocycloid is the path traced by a small circle rolling around the inside of a larger circle. Here is a VPython simulation of various hypocycloids. We define phi in such a way that phi equals pi when r equals the radius of the Earth. Also, phi equals 0 when r is at a minimum. And from here we are easily able to solve for the radius of the small circle, a, in terms of the radius of the Earth and r0. And finally, when phi is negative pi, r is again equal to the radius of the Earth. Note that these conditions correspond to our previous conditions of phi in the Brachistochrone problem. We'll find both the r and theta equations by using the geometry of the system. Therefore, we are able to get the r equation in terms of phi by simply using the cosine rule. To find the theta equation, we need to change the geometry slightly. It's fairly simple to show these expressions for tan of theta minus theta naught and tan of theta minus theta naught plus phi over 2. By plugging in the above equation, we can simplify further. By equating these two arc lengths, simplifying, and plugging into the above equation, we get our theta equation in terms of phi as desired. We have now shown that the path of least time between 2 points on Earth's surface is a hypocycloid. Okay, so we have two equations in terms of phi, and for the purpose of visualizing this system, we want these two equations to depend on time. So let's find the relationship between phi and time. We first need to recall our equations for time and dr d theta, and by plugging in and simplifying, we can find the equation for time in terms of r. By reintroducing the definition for our phi variable and substituting, we get the desired relationship between phi and time, which you can see is linear. We find the total time it takes the train to travel the length of the hypocycloid path by noting that phi ranges from negative pi to pi. Also note that pi times the square root of r over g is approximately 42.2 minutes, the time it takes the train to travel the length of the linear path. Here is a VPython simulation of the train moving along the hypocycloid path. And here is a comparison between a train moving along a linear path and a train moving along a hypocycloid path. You are able to see that the train moving along the hypocycloid path is much faster than the train moving along the linear path. Let's take a closer look at the differences between these two paths. This first graph is showing the times for each path at a given separation angle. The red line represents the linear path, and the blue line represents the hypocycloid path. For small angles, the hypocycloid path is significantly faster than the linear path. But as the angle of separation increases, the difference between the two times decreases. At an angle separation of pi, the two paths take the same amount of time. This is because the path of least time between 2 points that are antipodal of each other is a linear path through the center of Earth. This next graph shows the maximum depths of the two paths. We are able to see that the depth of the hypocycloid path changes linearly with the angle of separation. If we look at the difference of the two depths, we can see that the maximum occurs at an angle slightly less than pi over 2. Here is a graph showing the distance traveled by a train along these two paths. It's fairly obvious that the hypocycloid path, the blue line, is the longer path. Although, we find something interesting when we take a look at the difference between the two paths. We can see that, unlike the difference in depth, a maximum occurs closer to pi over 4. That's all I have so far on this topic, but stay tuned for the follow-up video where I'll analyze the effects of an Earth with non-uniform density on the linear path and the path of least time.